Welcome to DCL 601. This will be the first in a series on lightning protection, and grounding. I'm not going to go very in-depth on this. This will be just introductory concepts, and then I'll build on them as I normally do in later episodes. So just the basics today. I have 4 questions I wanted to address. Now these questions came to me almost 3 months ago in speaking with some new ham radio operators, and I realized they had some misconceptions about lightning itself. First of all, what's lightning? Well, we like to say lightning is electricity. I disagree with that, and let me explain what I'm really saying. You're probably familiar with the simple battery switch light bulb circuit. If the switch is open, the light doesn't come on, no current flows. It's very simple. Close the switch, current starts to flow, and the light comes on. This is an organized flow of electrons we would call electricity. Lightning is a discharge of charged particles that flow between the earth and clouds, or between cloud and another cloud. Now, it's true that huge amounts of electrons can flow in this exchange. To that extent, you could call it electricity. I call it an electrical discharge. Perhaps I'm splitting hairs here a little bit, but this is how I look at it. And frankly, in physics, this was how I was taught, that lightning is a discharge, where electricity is organized electron flow. What causes it to strike? Well, you and I both know that lightning tends to hit tall objects or high places. But we know from physics that lightning strikes when the potential difference between the cloud and ground, or an object on the ground, exceeds the breakdown voltage. This also can happen from cloud to cloud. This breakdown voltage can be as high as 3 million volts per meter. So for every meter the arc has to travel, it needs 3 million volts. So if we're going, say, 100 meters, we need 300 million volts total to get across the 100 meters. So that means lightning discharges are always very high voltage, tremendous voltage. However, is 3 million volts per meter required? Yes, except when it isn't. The 3 million volt per meter thing is a standard dry atmosphere number. And of course, during a thunderstorm, or in a thunderstorm, that's not a dry atmosphere. So the 3 million volts per meter is probably not required. It's, in all cases, you can have a discharge well under 3 million volts per meter. Of course, we don't really care what that voltage is. In a later episode, I'll talk about the current and the voltages you might encounter in the ground circuit in the equipment that you're trying to protect. Why does lightning seem to prefer to strike high places or tall objects? This is an interesting question. Let's take a look at this. There is a picnic pavilion made of metal, if you will, up on the hill. And then there's a radio tower down in the valley. Clearly, although the tower is much taller, about 3 times taller than the picnic pavilion, it's setting much lower than the picnic pavilion. Now, most of you watching this video intuitively know that picnic pavilions aren't struck by lightning very often, but radio towers can get clobbered multiple times in one thunderstorm. In the case that we show here, where would the lightning strike first? Because if you need a couple million volts per meter, you need slightly less voltage from the base of the cloud to the picnic pavilion than you would to the top of that little radio tower. So the pavilion would get hit more often, wouldn't it? Well, again, you and I both know that's not true. Why is that not true, though? What's really going on? Let's imagine we have two perfectly round conductive metal spheres. Let's charge them up. We'll make one very, very positive, which means the other one will look negative. Or better yet, we'll charge the one positive and we'll charge the other negative, so we get a really strong field. There will be electric lines of force between the two objects. Now, if you look closely, and I apologize, this is one of my scribbles. Essentially, the electric lines of force are spaced evenly around each sphere. Now, don't count the lines and don't really think about that, because in physics, we say that there are an infinite number of lines, but their intensity varies. So don't pay a whole lot of attention to how many lines there are. The point is, surface charge density is uniformly distributed on a conductive sphere. Generally on a non-conductive sphere as well, but let's just stick to a conductive sphere. Now, if that's true, what do you suppose happens if the spheres are of different sizes? You would get an effect somewhat like this. Now, there's probably a few more lines from the far side of the small circle doing a U-turn and coming back to the big circle. But as you can see, things are pretty even. What happens, though, if there is a metallic appendage attached to the bigger sphere? I said surface charge density is uniformly distributed on a conductive sphere. If this little appendage is also conductive, what would happen to the electric field? Well, there's an interesting little thing in physics where surface charge density is a function of the radius of the sphere. So there's effectively a very small radius right there. Smaller spheres exhibit a higher charge density. This is one of those non-intuitive things from physics. If you want to pursue this, just take what's on the screen right now at the bottom and pop it into Google and start doing a little homework. And you'll find out that I'm quoting physics theories. The point is, the higher the surface charge density, the stronger the electric field is going to be, even though the charge difference, the potential difference between the two spheres has not changed. So you end up with something like this. Notice how close the lines are to each other. This is a depiction of a higher electric field density at the top of that little appendage. Now, one thing you're probably thinking is, Mark, I think I know where you're going with this, and the Earth isn't a conductive sphere. I understand that. Give me a few minutes. So let's go back here. I talked about the effective radius of the sphere. Here we have two objects that have their own effective radius. The top of the tower and the picnic pavilion. Clearly the top of the tower is going to have a very small radius, tremendously small, compared to that picnic pavilion. Now, let me get away with pretending. Let's pretend that this is a magic cloud. And what's magic about it is at all times, the lower boundary of the cloud is perfectly flat and has the exact same charge all the way across. Obviously, this can't happen, but I'm using this as an example. Where would the first lightning bolt hit if the orange bar slowly increases in voltage? So there is a slow increase in potential difference between the surface of the Earth and that boundary of the cloud. Clearly, the picnic pavilion will require less voltage to form a discharge because there's less distance. However, what we will end up with, if we could see the electric field lines, and I can't draw all of them because, as I said, there's kind of like an infinite number, we would probably see something a little like this. Now, you see what's happening. The surface charge density at the top of the tower is causing a concentration of electric field lines. So in a very non-intuitive way, if you could measure the voltage between A and B, you would get a certain voltage. If you measured it between C and D, you would get a higher voltage. Now the voltage isn't really higher, it's just the density is higher. So you can see why the tower is going to get hit before that picnic pavilion. The 3 lines on the picnic pavilion and the 8 lines on the tower, obviously, as I said, you can't just count the lines. But my point is, there's a tremendous increase in field intensity at the top of the tower. Lightning does not strike an object because it is closer to the cloud. And lightning does not strike because the object is a conductor. Lightning strikes as a result of the concentration of field lines due to the surface charge density being so high at such a small radius as the top of the tower. When that potential gets high enough, breakdown will occur. The uneven distribution of surface charge density plays a huge role in the mechanism of lightning. If you sit back and watch a thunderstorm in an urban area with radio towers and tall buildings, you will see what I've depicted unfold right before your eyes. Now, let's look at one other little item here. Notice the space between the electric field lines around the tower. Notice how far you've got to go to get to another electric field line. This has been demonstrated to actually exist. That is, there is a cone or circle of protection around the tower. What I mean by that is if your ham station is really close to that tower, you can almost bet you're not going to get hit by lightning. Not directly. The lightning is going to hit the tower. So there's no reason for you to ground things. There's no reason for you to worry, right? Well, wrong. You are a tremendously strong target. While lightning will hit the tower before it'll hit you, the discharge of lightning creates what you might call an electromagnetic pulse that can be really strong. That can set out electric field lines that will induce a tremendous voltage in your antenna, coax, your antenna elements, things like that. So the idea of being close to the tall tower, yes, you're probably going to be saved from a direct hit most of the time, but you're not safe. Lightning damage can occur without a direct strike to your equipment. Are all antennas equally susceptible to a lightning strike? Well, yes, if lightning is going to strike wherever your antenna is hanging, doesn't really matter what antenna you have. Yes, if you have an antenna with a much smaller radius to it, effective radius, I suppose that could be a problem. But most antennas like vertical antennas or dipole antennas, that is vertical dipoles or ground planes, kind of have the same radius to them. Are all antennas equally susceptible to damage from a lightning strike? No. Consider this. Okay, we've got our tower. At the top of the tower, we've got a mast, and we've mounted our little ground plane antenna. And the radials and mount of the ground plane are bonded to the mast and the tower, which is very well grounded. But take a look, if you would, at the radiator. It has no path to ground. Its only path to ground is down the middle of the coax and down to your equipment. Not a good thing. Even if there's a lightning arrestor down at your equipment, you're really, really, really tempting fate here. Is there something you can do? Well, yes, there is. This is a simplified depiction of a 4-dipole commercial array that was popular in the 80s, 90s, and early 2000s. What I want you to notice is that the dipole loop, one end is bonded to the grounded structure. The other end goes to the center conductor. This is the kind of antenna we refer to as DC grounded. So the antenna element is at DC ground all the time. When you transmit and energize it with RF, RF current does flow here, back and forth through the element, and it radiates, of course. But what happens if lightning hits? Well, the one thing you'll notice is this pointy little thing at top. And remember that thing I said about small radius? The smallest radius object here is the little triangular cone. That little triangular cone is important. This antenna, if you've got a lightning arrestor on this cable down here at the base of the tower or at your radio station, and it's all well grounded to the same ground that the tower has, and it's a really good ground, you can take a direct lightning hit without equipment damage. In my years in the land mobile radio industry or two-way industry, I lost count of how many times we took one of these antennas down where everything was working fine. We were just moving the customer to a new site or whatever. We would take the antenna down, and lo and behold, this little cap was melted. It was clear that it had been hit by lightning multiple times, yet there was no equipment damage, and the customer did not have any high reflected power or any range problems. That shows you how effective it is if one of these DC grounded antennas, as I like to call them, if all of this is bonded well and the tower down below at the base is grounded very well and all your grounds are tied together, you can get away with a lot. I'm going to expand greatly on this concept in the next installment of this video series. That's it for this episode. I see I went 18 minutes, which is longer than I thought I would. I just wanted to talk about a few fundamentals. And then when we get into the next episode, I'll talk more about ground currents and grounding and things that are going on at the base of the tower, which is where you and I live, and it's where our equipment lives. I hope this was informative and helpful and fun, and I look forward to presenting the next one as soon as I can get it written and recorded. Thanks for watching, and I'll see you next time.